Yeah, so today we are going to discuss the topic amino acids and proteins. What are the amino acids? So generally here, the amino acids means the compounds, the organic compounds which are contains the amino and the acid groups here. Okay, so like the general molecular formula of the amino acid is where it is here, right? Amino group. So this is the general formula of the amino acid, COOH. Okay, so where it contains the amino group and the acid, carboxylic acid group. Okay, so it is called the amino acid. So in place of R group here, upon substitution of the variety of variety of substituents, so you will get the different amino acids here. And generally, here the amino acids, you know that it plays a very important role in the means it is a biomolecule. Okay, it is a biomolecule and it is playing a very important role in the formation of the proteins and the enzymes here. And you know the importance of the proteins here. Okay, so where the proteins are, we call the energy source. Okay, so the proteins are energy source here. By protein biosynthesis, you get the energy. Okay. And generally here, these proteins further modified into enzymes, and enzymes involves in the variety of reactions, metabolic reactions, okay, so some biological reactions here. And here the occurrence and structure and nomenclature of the amino acids. So generally, there are 23 in natural. There are 23 amino acids are available. Okay, 23 natural amino acids here. Right? Natural amino acids are available. And among these, we have classified these amino acids based on their structure, based on their occurrence here. Okay, so here is it is a general molecular formula of amino acid. Okay, so where here is the alpha carbon, and all 23 amino acids are alpha amino acids only. Okay, alpha amino acids means alpha amino means where the amino group is attached at alpha position. So with respect to of this carboxylic acid, this is the alpha carbon here. Okay, so where these functional groups, amino as well as the acid groups are attached on the alpha carbon. So we call these are the alpha amino acids. And here we classify these amino acids based on their occurrence, okay, and based on their structures. So based on these structures, we have the three types like uh, okay, so acidic amino acids, neutral amino acids, and basic amino acids. And based on their based on their availability occurrence here, we have classified in two types like essential amino acids and non-essential amino acids here. Okay, so out of 23, we have eight amino acids are essential amino acids here. And what are the essential amino acids and what are the non-essential amino acids generally? So essential amino acids means which are not produced in the body. Okay, our body is not produced the amino acids, so those amino acids are called the essential amino acids because they are not produced. So you need to take these amino acids from outside in the form of right means you take it as the supplement. You take it in the form of okay medicines or you take it is in the form of some supplements. Okay, you take from the outside. Okay, and essential amino acids and non-essential amino acids. Non-essential amino acids means they are produced in the body. Your body is going to produce these amino acids. So you means we no need to take these amino acids from the outside. So those called the non-essential amino acids here. And here is some structures of amino acids. Okay, so like here in the general molecular formula, so in place of R, okay, here is a NH2, H, here is R here, and COOH. So if R is substituted with hydrogen, okay, in place of R, if you keep the hydrogen, then it is glycine. Right? Very starting the first amino acid here. Okay, where generally out of 23, only glycine is a chiral amino acid. Generally, the amino acids are chiral in nature. Chiral means you know that where the central carbon atom is surrounded with four different groups here. Okay, but if you see the glycine structure, okay, it don't have the chiral groups here. Okay, so you just here is a next to here is a hydrogen and hydrogens COOH. So here these two homotopic hydrogens are there, right? These two hydrogens are homotopic in nature. Okay, so it is not a chiral one. It is a achiral carbon. And in place of R, if you give that methyl group here, then it is alanine. Okay, so in the place of R, if you keep the methyl, so it is alanine. And the abbreviation is it is ALA. Okay, glycine. For glycine, the abbreviation is gly. And in place of R, if you keep that isopropyl group here, right? So isopropyl group, right? So R is isopropyl group. So it is so it is valine. And if it is a secondary butyl group, then it is leucine here. So like that, upon substitution of the variety of groups here, so we'll get the different amino acids here in the general molecular formula. If you substitute the R group with the different substituents, we get different amino acids. And the abbreviations of variety of amino acids you can see here. Like if you to this particular right, alanine. Okay, so one of the hydrogen from the alanine methyl group, one of the hydrogen is substituted with phenyl group. Then it is phenylalanine, right? And the proline, there is a heterocyclic amino acid. Okay, proline is a heterocyclic amino acid here. And here some other amino acids also there. So in this table, we have the all the amino acids structures and their abbreviations here. So here, and we have the cysteine, right? So very important thing here. So where the cysteine is having the sulfur, right? Cysteine is having the sulfur moiety, and methionine also having the sulfur here. Okay, so methionine and cysteine is having the sulfur atoms in the part of that structure. Okay, leucine isolate. So these are some amino acids which we have the different amino acid structures here. Okay. And as I told you in the beginning, where these amino acids are chiral in nature here, except the glycine. They will right. So rotate the plane polarized light. Okay, the chiral mean where the compound, right? The chiral compound able to rotate the plane polarized light towards either left side or the right side. Okay, so you know that this is the, for example, here this is PPL, plane polarized light here. Okay, So when we right, so place this compound in a polarimeter here, right? So in a polarimeter, then the compound based on their nature, right? So it will be either it is rotate this light. Okay, this is in the right standard mode. So either it is rotates towards the right side, or it may be rotates towards the left side here. So if any compound which is rotating the PPL, right, towards the right side, it is called the D, and okay, D amino acid. And if any compound which is able to rotate that light towards the left side, then it is called the L. Okay, so D and L. Okay, so DL nomenclature is assigned to this. And here, yeah, now the synthesis of amino acids, alpha amino acids. You know, all are alpha amino acids only. We don't have other amino acids. All are alpha amino acids only. And here the amino acid synthesis is done by some chemical reactions. The first method is to synthesize the alpha amino acid. The amination of lactic, yeah, the amination of these halo acids. Okay, amination of the halo acids. Generally, we call it is a HVZ reaction. Helmholtz Zielinski synthesis. Okay, this one HVZ. Very important synthesis method and very important reaction. So, but here the where this method is involving, okay, so the substitution of the amino group with the bromine. So in the HVZ reaction, Helmholtz Zielinski synthesis. So where here is a right with this particular okay carboxylic acid when it is brominating, right, when it is brominating here, so you get the alpha bromo carboxylic acid, and this alpha bromo carboxylic acid further reacts with the excess of ammonia solution, excess of ammonia solution. Then this particular, right, so NS2 is going to replace, substitute this bromine. Then what is going to obtain here? So we are getting this alpha amino, okay, alpha amino, the carboxylic acid here. Generally, it is alpha amino acid. So in this way, you can synthesize a variety of alpha amino acids by amination of the halo acids, carboxylic acid. And another method to synthesis of amino acid is the Gabriel Thallimide synthesis, right? So this is also one of the important synthetic method. So where this Gabriel Thallimide synthesis, where this alpha amino acids are synthesized by this reaction with the alpha bromose substitution, right? So like the HVZ reaction here also where we are substituting that particular bromine with some amino group here, right? So here thalidomide is taken. Okay, so in this reaction where the this is your thalidomide. Okay, Gabriel thalidomide synthesis. Right? So Gabriel is a scientist name here. So yeah, thalidomide is first it is thalidomide is converting into the potassium salt of thalidomide by treating with like potassium hydroxide or any other right salts here, KCl, okay, potassium chloride or potassium hydroxide, whatever. So first you have to convert this particular thalidomide into potassium salt of phthalimide here. Okay, then it is going to treat with this ester, bromo ester here, alpha bromo propionate here. So where we are taking this alpha bromo propionate. Then right. So where this particular alpha bromo propionate is uh, gets substituted with this particular potassium salt of phthalimide here. Okay, so KBr by the mole of the minus KBr here. So we get the N substituted the phthalimide. Okay, N substituted phthalimide is obtained as a intermediate compound. Right? So then upon hydrolysis, okay, upon hydrolysis here, so where this particular, right, so this compound is going to, right, so upon cleavage of this bond, upon cleavage of this particular amide bond here, okay, so this amide means phthalimide, the amide bond is going to cleave upon hydrolysis and it is giving your, okay, phthalic acid, okay, this is your phthalic acid here and the alpha amino acid is obtained, this is your amino acid. And some the fractional amount of the ethyl alcohol is obtained. So this is Gabriel Thalymide method, right? Very simple and very important also, where the phthalimide initially it is converting into potassium salt of phthalimide here. Then the alpha bromo ester is gets substitute means attached with this particular potassium salt of phthalimide. Okay, then upon hydrolysis, where this the amide hydrolysis is takes place, and it is going to convert as a alpha amino acid and the phthalic acid and ethyl alcohol. Yeah, the main product is your alpha amino acid. Then the phthalic acid and the ethyl alcohol is obtained as a byproducts in this particular reaction. And you can take one more example, means by substituting the R group here. So we will get a variety of compounds. And next, the synthesis of alpha amino acids from the malonic ester. Okay, so by malonyl ester, here the diester. So also you can get this alpha amino acid. Here what we are taking, just the diester, malonic ester is taken, and with the here bromination. Okay, the malonic ester, you know that so this is methylene group. Okay, so this is methylene group, very acidic methylene group. Okay, very active. We call the active hydrogens. These two are the active hydrogens here because right, so the alpha hydrogens, these two alpha hydrogens are very active. Okay, active hydrogens. So where the bromine substitution, right, that the active hydrogen substitution is takes place by the bromine in the CCl4 solvent here, and we get the alpha bromo diester malonic ester here, and this alpha bromo malonic ester is further treated with the potassium salt of phthalimide, like in the phthalimide Gabriel method. Okay, so the substitution, N substitution is takes place here. N substitution is takes place, and we got the intermediate compound as that N thalimido malonic ester, right? N thalimido malonic ester, and this N thalimido malonic ester by treating with the base. Okay, so base where the abstraction of this acidic proton is take one more acidic proton. Okay, so one acidic proton is substituted with the bromine, and then upon attachment of this particular N-bromomelonic ester with phthalimide, potassium salt of phthalimide, then by treating with base, we are abstracting the one more acidic proton here, right? And we are converting this carbanion. The carbanion is generated, and this carbanion further reacting with the alkyl halide. Okay, so with the alkyl halide, so you will get this particular, right? So you will get this particular R substituted the intermediate compound. And upon hydrolysis, right, finally by doing the hydrolysis, where this cleavage of this bond is takes place, and we get this alpha amino acid, right? And you get this particular phthalic acid is a byproduct in this reaction, right? Upon treating means heating with the water, right? So you get the alpha amino acid. So in place of R, right? So you can take variety of substituents and you can generate or you can synthesize the variety of amino acids here. For example, if in the Rx, right? If you take the methyl halide like chlorine or bromine, then what you get here? So you will get the alanine here. Okay. And if you take the right, so if you take the right, so the phenyl, right, so benzyl chloride, you will get the phenylalanine. Okay, so like that, you can synthesize the different amino acids by this particular uh, malonic ester synthesis of the amino acids. Here, well, right. So by this method, where we have synthesized a variety of amino acids here, right? So like by this particular N uh, malonic diester, okay, N substituted on this phthalimide, right? So where by treating with the base sodium methoxide and some halo substitution here, halo alkyl halide here. Okay, so we are getting the aspartic acid, right? And same thing here, the benzyl chloride, we are getting phenylalanine here, right? Where you get the 64 percentage of yield. So like that, by substitute by in place of R group here, so you can take variety of amino acids, variety of substituents, and you can synthesize the different amino acids here, right? And upon taking this, right, some unsaturated compounds also, you will get the glutamic acid, right? And here is what we are taking, just we are getting methionine. So only thing is you first you abstract this proton by base by treating with the sodium methoxide or sodium methoxide, right? Then you generate the carbon ion. Then you treat with the alkyl halide, right? So here we are taking this sulfur, right, derivative. So we are getting this methionine where the sulfur we have two sulfur containing amino acids like right. So here the cysteine and methionine, isn't it? So like this, we'll get the different amino acids by this malonic ester synthesis. Next, one more method is Strecker's method. Strecker's method. So this is also one of the important synthetic methods of amino acid. In the Strecker's methods, what we are taking? We are taking the aldehyde and ammonia and hydrogen cyanide, HCl. So first, initially we get this amino nitrile cyanide here, and this nitrile is converting means upon hydrolysis, it is going to convert as a alpha amino acid. Okay, this is Strecker's method, right? So what are the reactants in this method? Aldehyde here, aldehyde, okay, aldehyde, and the ammonia and hydrogen cyanide, right? So first we are by nucleophilic substitution reactions. Okay, so here is a uh, so is aldehyde, right? So here is ammonia, right? So where this ammonia is going to, right? So nucleophilic addition reactions takes place, and what you are getting here, the hydroxy amine. Okay, so hydroxy amines takes place here. Okay, so then here the treating with HCl, right? HCl by where the Cn minus, it is nucleophile. So where it is substitute the hydroxy group here, and it is going to convert as a cyanide. Okay, amino nitrile are the cyanide here. And this cyanide, further upon hydrolysis, it converts into, right? So like cyanide, it is converting to carboxylic acid. Nitrile hydrolysis gives the carboxylic acid here. Next, the physical properties of these amino acids. So generally here the amino acids, these are the crystalline colorless compounds here, and these are soluble in water because the amino acids, right, having the polar groups, so they are easily soluble in water here, and it is sparingly soluble in the organic solvents like chloroform, acetone, right, ethyl alcohol, methyl alcohol, carbon tetrachloride, right? So sparingly soluble, but it is easily soluble in the water. And generally here, yeah. So in the UV spectra, you can identify these uh, amino acids, right? So by IR spectra here. So IR spectra generally the absorption, right? The absorption band for this IR spectra is, it is because it is having the amino group and the acid group, right? So amino groups will be the functional group. The characteristic absorption band is obtained at 3140 to 3000, right? So in the IR spectra, you can know that, you know that, so yeah, right? So, right. So it is appears at 3130, right? So in the range of 3000 to 3130. And here the carbonyl, right? The acid carbonyl group is 10 at 1600 to 1500 centimeter inverse here, right? Generally, the carbonyl CO, right? So CO group is obtained in the range of the 1595 to 1700 actually. So here, because it is having CO minus group, so CO group, so will be appears in the range of this particular 1500 to 1600. And in the UV spectra, so the band, okay, the lambda maximum is obtained at to 250 nanometer. Next, the chemical properties of this amino acids. So chemical properties here, the we have different reactions by involvement of the different groups here. So the reactions involving due to the amino group here, and the reactions involving due to that carboxylic acid group, and the reactions involving that the CH, okay, the CH2 group. So first we'll see the reactions involving the amino group. So here, if you take the glycine, okay, so simple treating with HCl, hydrogen chloride. So where the amino acid, the glycine is, upon reacting with HCl, is converting into glycine hydrogen chloride. It is salt formation, right? And generally here it is in the salt form, so it is sparingly, right? So it is soluble in the water. And when this particular amino group is treated with, right? So acid chloride, CS3, COCl, okay, acetyl chloride here. or acetic anhydride. Right? Acetylation reaction is taking place where this particular amino group is converting into amide. Okay, amino group is converting into amide here. Amide formation. You can take the N-acetyl glycine. You get the N-acetyl glycine here, where the substitution, nucleophilic substitution reaction is taking place. Because here the acetyl chloride, it is having the electrophilic carbonyl center here, where the NH2 group is, okay, so this NH2 group is, okay, so it is attacking at the electrophilic carbonyl center and it expels the chlorine. It expels the chlorine here. And here this glycine, upon treating with the benzyl chloride, okay, so upon treating with benzyl, PHCOCl here. So you will get the hippuric acid, N-benzoyl glycine. We call the N-benzoyl glycine here. And this is a hippuric acid. Right? So in the presence of some base like NaOH here. So why you are using NaOH or any base here? Because here in the amino acid, okay, so where are there is amino group as well as the acid group. Both are active in nature, right? So generally when this NH2 group is reacting with this COCl, then you get the hippuric acid. And one more possibility is there where the COO minus, where this is also acting as a nucleophile and it is going to attack at this particular carbonyl center. Right? So then what happens here? You will get the ester. Okay, you get the ester compound. So some side product is forming. So to avoid this problem, so we treat with the sodium hydroxide and we are making this acid group as a salt here, right? CO minus Na plus. So we are making the inactive, this terminal, carbonyl terminal becoming inactive. So only the amino group is in the active form. It is free in form. So it is going to attack, means react with your benzoyl chloride and you get the benzoyl glycine or your hippuric acid here. And oxidation reaction with the nitrous acid here. So here the amino acid, when it is reacting with the nitrous acid in HCl, so it gives a diazonium salt. Okay, it gives a diazonium salt here. And diazonium salt further upon hydrolysis, where it is going to convert as a lactic acid by liberation of the chlorine and nitrogen gas. So it is going to converting as a lactic acid here. Next, nitrosyl chloride, right? So amino acid upon treating with nitrosyl chloride, NOCl. So where by removal of water and nitrogen gas, it is going to produce a chloroacetic acid. Okay. So in this way, we have the variety of amino group involving reactions here. And one more reaction with this amino acid involving reacting with the hydrogen iodide here. So we get this beta phenyl propionate acid. And the second part of this chemical reaction is the reactions due to the carboxylic acid group, the involvement of the carboxylic acid group. So here, right? So here the amino acids generally will form the salts with heavy metals here. Here what we are taking some a copper salt of glycine, where because it is complex here, so it is having the very deep blue color needles here, right? So copper salt of glycine. Okay, so because it is a coordinated complex. Okay, so it has some colorization. So it it is heating with copper oxide CuO with an aqueous solution of glycine here. So it is giving some complex. Okay, so here is a glycine. When it is treating with this particular copper oxide, so we are getting this copper salt of glycine with the deep uh, blue color. Next, with this particular glycine is reacting with alcohol, right? Ethyl alcohol here. So it is giving some, right, with the okay, so you get some what is it? Bitter ion is obtained, right? Here NH3 plus Cl minus. So some uh, what is that? Polar group is obtained, dipolar group, and where this acid group is right gets esterified, and you will get the ester derivative. And by treating with sodium carbonate base, right? So where this okay, so the this particular dipolar, right, NH3Cl, NH3Cl is neutralized, and you will get this particular ethyl ester of glycine product here. And this carboxylic acid, when it is gets reduced with lithium aluminum hydride, so you will get the beta amino ethanol, right? So beta amino ethanol is obtained by treating with the non-selective reducing agent lithium aluminum hydride. Right? You know that lithium aluminum hydride is non-selective reducing agent, very highly uh, right, strong reducing agents. We have the sodium borohydride and the lithium aluminum hydride, two reducing agents here, nucleophilic reducing agents. So sodium borohydride, it is very weak reducing agent, where lithium aluminum hydride is a strong reducing agent here. So you will get this particular beta amino ethanol, and this alanine or the amino acid, alpha amino acid, when it is treated with phosphorus pentachloride here, PCl5, so it gives some acid chloride, and phosphorus chloride is a byproduct here, right? So PCl5. So it is giving the converting acid group is converting as a acid chloride, COCl here, right? And the alpha amino acid is when it is treated with barium oxide. Okay, so heating with barium oxide, so it leads to decarboxylation, right? Leads to decarboxylation, and is giving the alkyl amines here, right? The simple amines is obtained. And next, the reactions involving both amino and acid groups. So both amino acid and acid group involvement reactions. Say, here the amino acids, right? So the internal they will exchange the proton. By exchanging the protons here, they will convert as a Zwitter ion here, right? So yeah, due to this reason, so they have the high melting points here. Right? So with they have the large dipole moment, right? High melting point and solubility, right? That's means difficult of the solubility in the water, right? So due to the reason for this, they are forming the Zwitter ion. So Zwitter ion generally they are right. How they are going to form here? Where the hydrogen, right? So the acidic hydrogen in the carboxylic acid is exchanged with this particular NH2, and it is going to form the CO minus and NH3 plus here. We call this the Zwitter ion. So the characterization of this amino acids, identification of the amino acids here. So generally, we can identify these amino acids by nin-hydrogen reaction. So here the nin-hydrogen reaction. So when an aqueous solution of the amino acid is treated with the uh, triketo hydrogen hydride here, we call this the simply it is called the nin-hydrogen. The nin-hydrogen, the chemical name is triketo hydrogen rin hydride, right? So a violet color is produced. This is the nin-hydrogen reaction. So you can means it is a characterization reaction of the amino acids. You can identify the this amino acids, variety of amino acids with this nin-hydrogen reaction. So here the violet colored solution shows a absorption maximum at 570 nanometer in the UV region, and the intensity of this absorption is proportional to the amount of alpha amino acid is present. Okay, so ninhydrin is an important reagent in identification of estimation of alpha amino acids. Next, peptide structure and nomenclature. So generally here, the alpha means amino acids, right? Combined together, they will form say peptides, right? So peptide means NHCO. Is called the peptide. Okay, so this is a sorry, right? So this is peptide where the amino acid is involving in the amide bond formation. We call this is the peptide. Okay, so here is the two amino acids are involving to form a peptide. So we call it is a dipeptide. And if three amino acids are involving, we call the tripeptide here. Three amino acids are involving, we call the tetrapeptide. So like that. Okay, so we get the polypeptide here. And generally this polypeptide is called the proteins. Right? So the combination of these amino acids by removal of water, right? So we get this peptides, polypeptides here. So for example, here the two amino acids which are taken the glycine and alanine here, right? Glycine and alanine, and we get this dipeptide, and this nomenclature is glyala, right? So glyala. Gly means glycine, ala means alanine here. This is the peptide nomenclature, right? And here is a tripeptide with the glycinyl phenyl alanine, right? Sorry, it is tetrapeptide. One, two, glycinyl phenyl alanine, glycine. So tripeptide, right? So tripeptide we get by combination of the three amino acids here. And here is a tetrapeptide with the glycinyl phenyl alanine seryl glycine. Right? So like that. So based on the combination of amino acids, so we'll give the nomenclature, right? So by combination of this amino acid, we give the nomenclature of this one, right? For example, if like you can produce a polypeptide like alanine, okay, is less. You take valine here, okay, and some phenylalanine, right? So alanine structure, you know that, right? So here it's a so NH2 and COOH here, CH. This is alanine. Then we are taking the phenylalanine. So one of the hydrogen is replaced with the phenyl. So it is phenylalanine. And one more is the valine. So valine is isopropyl group here. So here is a isopropyl group is there, right? CS3, CS3. So by combination of these three, you will get a tripeptide. Okay. So then its name will be the ala, okay, phenyl ala and valine. So alanine, phenyl alanine, valine. Right. So like this, you can get the variety of peptides here. Right. So this is the peptide nomenclature. Next, yeah, proteins. So here the proteins. So generally here the basic unit for these proteins are the amino acids only. Right. So here the amino acids are combined together and it is forming the polypeptide. And this polypeptide, right, it is modifying as the proteins. And these proteins further modified as the enzymes here. Okay, so the basic unit for these proteins and enzymes are amino acids only. Okay, so here the protein generally proteus. Proteus means first here, right? So it is a Greek word where it is proteins is uh, protein nomenclature is taken from the Greek language. So as per this Greek, proteus means the first here, right? The polymer. So first the polymer structure is called the protein. And generally here it is a thread-like structure. Proteins are the thread-like thread-like structure here. Okay, no geometry for this proteins here. A specific geometry because it is a huge compound, highly complex compound here. So no particular geometry is you cannot see the particular geometry. Right? So for the giant complex structures, you cannot assign the geometry. Okay, yeah, and this proteins generally, right? So the structure will be assigned based on their structure. Here we have the three means based on the generation here. Okay, so primary structure, secondary structure, and tertiary structures are assigned to this one. And here the primary structure of protein is very simple structure, right? Very simple structure. You can easily means you can the peptide bonds are easily visible here, and you can easily identify the peptides between the amino acids here. So that is a primary structure, means very simple structure. And going to further where the complexity is increasing, like in the secondary structure, somewhat complex than your primary structure here. And tertiary structure, it is highly complex structure, right? And its molecular weight will be huge. Here you can see the right. So secondary structure. So you can see the secondary structure of these proteins, right? So here the peptides are visible, and you can see the hydrogen bonding between the carboxylic acid group and amino groups here, right? Like in the DNA, right? So polypeptide. So you can have the hydrogen bonding between the this carboxylic acid group and amino group here. And if you see the tertiary structure of this one, so it is very complex structure. This is somewhat complex than your primary structure. And here also the visibility, right? So some clear visibility is there, the structure. But if you see the tertiary structure here, very complex structure and very, what is that? So the zigzag structure is there, right? You cannot, means the structure and the bonding between the groups is not clearly visible, right? So that is the tertiary structure. So based on their complexity, we can classify it into primary structure of protein, secondary and tertiary structure. So very, very important here, the structure of the protein, primary structure, secondary and tertiary structure. So, okay, time is up. So I'm stopping here.